What is a graph? Graph is a data structure. Right? You have seen, I think in the last chapters, you have seen a lot of arrays, right? We have used a lot of arrays in different problems. This is a data structure. List is another data structure, okay? But these kind of basic data structures will not be able to solve a certain problem, okay? We will look at what are the real-time problems, okay? To solve any of the problems that we discuss in further slides, we need a special type of data structure, okay? Because you have to not just represent that element. Like in array, what we did, we said, okay, there is one element 10, there is another element 20, right? But you're not showing the relationship between these elements. We don't know that. However, in the graph, apart from just telling the value of that element, you have to show the relationship to some other element, okay? You have to say, this is connected, like this, it is connected, right? So there is also a relationship. Now, to represent that relationship, we need a new data structure. That is why we cannot go with the basic data structure. So this data structure consists of a few attributes, okay? When you say graph, it will always have a vertex, it will always have an edge. Vertex are these endpoints, right? These endpoints are your vertex. This line between connecting two vertex. So vertex means singular. When I say vertices, it is plural. This is the plural form. This is the singular form. So edge connects two vertices, right? This is one edge. This is one edge. Basically, you take any two vertex, you have a connectivity between two vertex. So this is an edge. Okay. You can also number the vertex, because here you will not know it is connecting what to what. So you can either number them. You can also use alphabets. Like for example, I can use A, B, C, like this. Okay. The vertex can be labeled. You can use number or alphabets to label. Okay. Now, what is the property of the edge? Edge, it not just shows that it is connecting two vertices, it can also have a property of weight. Okay, there is a weight property. Weight means what? How much cost it takes to go from vertex 1 to 2. It takes cost 10. Okay, you will be able to appreciate this down later. We have some examples. We will see how this will be used. But you can just understand for now that an edge has something called weight. Okay. Okay, what is the, so we looked at graph, right? Now we'll see all the different subtypes, like different types of graphs, okay? So one type of graph is a connected graph. Connected graph means what? All the vertices are connected. Like for example, if I have A, B, C, D, E, right? Like this, okay? Is this a connected graph? Yes, no? So this is a graph, okay? Is this a connected graph? Because this one, E is a standalone vertex. It is not connecting to any edge. So this is not a connect. So if you want to make it connected, it should have some connection from any vertex, right? Now, this graph is a connected graph, okay? Now let's look at real-time examples. So it is used in transportation, right? You have different places. You want to go from one place to another, right? You need to know whether you have, suppose you want to take a bus. Okay. Say I want to come from, say, Yeshwantpur to JP Nagar, right? How will I come? I need to see whether there is any, which way, which bus I need to take. Is there a bus which goes directly from Yeshwantpur to JP Nagar? So I can take, yeah, there is a bus from Yeshwantpur to JP Nagar. I can take that bus, right? Suppose there is no path here, right? Suppose this is not there, right? So if I have to go from Yeshwantpur to JP Nagar, how can I go? This is option 1. Is there any other way?
Yes, ma'am.
Yeah. So I can also go to, I'll call this as P. Okay, I can go to KR-Pura. From there, I can go to JP Nagar. Route is also possible. Okay. So in real-time examples, if you have a graph, it is very easy for you to find the route. And it is used in all kinds of transportations. Like you can have the bus route. Now you have metro, right? So you have the metro route, you have the train route. You also have the airplane routes, right? From which city to which city you have actually flights. So it is used in transportation. I think this is one of our metro maps only. So if you look at it, each of these places, right, you can treat it like a vertex. So you can say that if you want to go from here to here, you have to take this route, right? So if you see those dots are nothing but your vertex, right? And these are your edges, right? So very easily simulated. Your real-time example is very easily simulated using graphs. It is. Okay, what are the other ways in which graph is used? Okay, the other one is human interactions. When I say human interactions, today we have a lot of applications, right? We are actually connecting to WhatsApp. We have Facebook, Twitter. I don't know how many of you are there in LinkedIn. Have you seen this? Like the moment you connect to somebody, it will tell you, do you want to connect to these people? It will give you those suggestions. How it does that is basically it knows, use these attributes and make suggestions. It says, okay, now you are connected to this. Okay, there is something common between this and these set of people also. Are you interested to connect? Right? When it proposes me that I may be interested, so I'll go ahead and connect. Right? I'll also make connections. Very realistic examples. So that's one very good example of graphs. It is also used in electronic circuit boards. So if anybody you have friends with electronics people, you may discuss with them. Basically on a PCB, right, printed circuit board, you'll have a lot of electronic circuits to place it, right? You need to show which one is connected, how is it connected, right? And how is the placement also is very important on PCB, right? So that can be very easily represented in a graph. Electronic circuit. Telecommunications, one of my favorite. I mean, this is where I actually work on. My work is related to telecom domain. And graph is basically used literally the core of it, right? Okay. Why do we use this? When I say telecom, right? You all, if you have internet connections at your home, right? So you may have some, say, or let's take your cell phone towers, right? So you may have a tower here. You may have an Airtel tower here. So Airtel tower 1, right? Now in the vicinity, this Airtel tower may have a coverage of say some, say 2 kilometers. Okay, so if your houses are located within this, you will be actually, when you switch on your phones, you will be actually getting connected to this Airtel network. Right now, the moment you go out of this network, right, you may be, when you start using your mobile data, you will actually be connected to a different tower. Right. So to say this, that given this tower, what are its connections, right? And also a network element. This can be treated like a router. Say if you have a router at home or even in your college, right? You may have a router. You have to say that, okay, say you have 2 labs. You have lab 1, lab 2. I'm sure there are other places. I'm not sure if library has internet access. So you may have other places also where internet access is there, right? So how is this access provided? You will have some router 3, right? So you will have some connectivity here, right? So this again, you can represent it through graph. You can say, how is your network connected, right? If you look at this is how your probably a Airtel or a Geo network will look like. It has like so many connections, right? So you can actually zoom into your network, and this is a real-time example. Okay. So now that we have understood on the usages of the graph, let us see different types of graphs are there, okay, to solve different concerns or to solve different issues. So let's look at all the definitions. Directed, undirected. Directed means if I have to go from A to B, I have to take this path. Okay, there is a direction. When I say A to B, here I can reach from A to B. Can I go from B to A here? Can I reach from B? Can I go to A in a directed graph of this one? Yes, no. Can I go from B to A?
No, ma'am.
No, you cannot go, right? In a directed graph, the path is very fixed, very defined. Okay, the path, wherever the arrow is, only that direction you can go. And in a directed graph, this is called your source. This is called your destination. Okay, you can call it destination, or it is also called as target node, right? Source and destination. You always, only if you have here, you can go from here to here. Okay. However, in an undirected graph, I can go from A to B. I can go from B to A also. There is no restriction on direction. So when there is no arrow put, you can also represent this as I have A to B and I have B to A. So your undirected means something like this. Okay. Let's look at one more. These are all very self-describing. Connected, disconnected. Look at the diagram you can make out. Connected, all vertices are connected. Disconnected, one or more. So I asked you this question earlier also. I can have, even if one vertex is not connected, this is a disconnected graph. Okay. Okay. Let's go to minimally connected. Minimally connected means I may have 4 vertices. Okay. I don't have to like, what is the minimum set of edges I need to connect all the vertex, right? Like for example, if you see this is connected, right? And minimum I need 3, right? I need 3 edges to connect this graph, right? Whereas I can also have like more connections, doesn't matter, right? I can have like this also, but minimum you need to have so many edges to connect this. Okay, so I hope you are clear with what is minimally connected. Strongly connected comes only in directed graph. Strongly connected means you have both ways. Like I said, no, here you can go from A to B, but you cannot go from B to A, right? This is not possible. So if you have a connection where you can go from B to C and you can go from C to B, this is called a strongly connected graph. And it comes only in the directed graph, this concept of strongly connected. Okay. Stop me anywhere you don't understand, because this is all theory. I'm just going ahead, but you can stop me. Okay, this is very important. I told you, right? Edge have a property of a weight, right? So you can represent a graph with weights, or you can represent a graph without weights. Okay, different use cases. So let's go back to the examples that we saw, right? Okay, look at this human interactions, right? All I need to know is whether I'm connected or not. Okay, it really doesn't, I don't need any weight on this edges. Okay, I just need a connection to say that, yeah, we are connected. However, if you look at this example, right, here weight is important because I may be I may be going through a bus, or I may be going through my own vehicle. In both the ways, right, I'm spending my money, right? If I have to go, I have to spend some money here and I have to spend some money here. Either it could be a bus ticket or petrol cost, right? So in these cases, the weight is important. Okay, like we said these 3 routes, right? How is the weight used? I'll tell you. So if you go from Yeshwanthpur to Kiarpuram, Kengeri, I have to travel 25 kilometers. Okay. Then if I go from Kengeri to JP Nagar, I have to travel 15 kilometers. So the cost for me here is 40. Okay, it can either be distance or it can be the money that you spend, right? Different units can be, but anyways, it's 40. If I take this route, Yeshwanthpur to KR to JP Nagar, so I will be 22. So here the cost will be 45. So now you can appreciate the difference between when I need a weighted graph, okay, in cases of transportation, where I want to know how much distance it takes, right? I will need some weight. Here, I don't need a weight, okay? Telecommunications, generally, we will need weight because it depends on your fiber length also, right? Suppose your lab 1, lab 2 is closely connected, right? So I will give a weight of 10. Now, but your lab and library are very far connected. I'll give a cost of 40 because a cost could be that it's very difficult to connect these two, or it may take a longer cable, right? Depending on different reasons, definitely this connection is more a heavy weight than this connection, right? So even in telecommunications, weighted graphs are used. Okay. Subgraph is just a subset, right? It may not connect all the vertex. Like here I have A, B, C, D, but in the subgraph I just have A, C, D. But A, C, D is a subset of it, right? It is from here to here, here to here, right? So it's a subset of the main graph. Similarly, B, C, D, right? If I look at it, B, C, D, right? This is also a subset of the main graph. Concept of path. Path means you will go from one vertex to another vertex, and you have to tell I'm taking this edge 1. Then I go to this one. You have to tell that I'm taking this edge 2. So your path will be something like this. You can either say YKJ, okay, or you can say E1, E2. Right? Different ways of representing your path. But path always has a source and a destination. You need this to find a path. You cannot just say, give me a path. You have to tell where I should start, where I should finish. You give me that, then I will tell you the path. Okay. Okay. Different types of path: simple path, cyclic path. Okay. Simple path is where your vertices are not repeated. Right. We gave that example, no? Yeshwanthpur to Kengeri to JP Nagar. Okay. But say that person had some work in what was that? KR also. They finished that and then they came back to JP Nagar. Right. So I'll put it like this. They finished the work in KR and then they came back to JP Nagar. Right. So if you see here, JP Nagar, this vertex is repeated. Right. So this is not a simple path. In a simple path, vertices are not repeated. Right. So if you look at this example, yeah, let's look at this. So 1, 4, 5, 7, 6. What is this? 1 to 4. This one. 1, 4, 4 to 5, 5 to 7, 7 to 6. So any of your vertices are repeated here? No, right? So this is a simple path. Let's look at one more path. Let's see. It says 1 to 4. Okay. 4 to 5. Okay. 5 to 7. Okay. 7 to 4. I'm going back here. Right. 7 to 4. Then 4 to 3. Then 3 to 6. Right. So if you look at this, there is this vertex which is repeated. Right. I have this vertex repeated twice. So this is not a simple path. Okay. Same thing with the, okay, in a path, right? Say, how can I give this example? Anytime you have done a roundabout, okay. I think one example I can think of is say you have to invite somebody. Say you're hosting some party at your home, okay, some function at your home. So you have your home here, okay. you have to go meet people, right? So you go to place 1, you go to place 2, right? You go to place 3. After doing all that, you come back to your home, right? This is one example we can directly connect to. So you could have paths. So here, what is the path? I went from H to P1, then I went to P2, then I went to P3, and then I came back to H. So in this case, my source and destination are the same. So I can also represent it like a cycle, right? It's a cycle. So cycle means what? It's a path where my source and destination are same. Okay. So in cycle also we have this concept of simple and non-simple cycles. Started from 1, you went all the places and you came back to 1. So this is a simple cycle because here your vertices are not repeated. Okay. Now what is a non-simple cycle? Say you start at 1. Okay. You went to 4. I'm just redrawing this diagram here. 4. You went to 5. You came back to 4. Okay. Then you went to 3. And then you went to 1. Right. So you started at 1. You came back at 1. But here you have some vertices repeated. So the moment you have a vertices repeated, it is not simple. Okay. Last concept of a loop. A loop is you start at a vertex, you come back to the same vertex. Okay, this is a loop. Okay, so you have one edge. Okay, so if you look at it, 2, you have one edge, but you're connecting to the same 2. Right? This is a loop. So there are 2 ways of representing graph data structure. One is a matrix and the other one is a list. Matrix means arrays. Okay, and list